Hey guys, alright, I'm on the wrong page, going to do a quick lesson about implicit differentiation. That sounds awesome, right? Okay, so first I want you guys to think about the definitions of implicit and explicit. Now, when I say explicit, you guys think like, oh, that new album I got was marked E for explicit, right? That's not really what we're talking about here, okay? Implicit is like implied, kind of. Explicit is just done, right? So if I explicitly tell you to do something, I'm like, I want you to take out your pencil and put it on paper and take notes. That's explicit. Implicit is kind of a little bit like fancier, a little bit more implied. Okay, all the derivatives we've done so far have been explicit equations. So some of the derivatives like y equals x squared, that's explicit. Y equals x over x minus 1, that's a quotient rule, that's explicit. That's your chain rule. They explicitly express y in terms of x. Okay? In this lesson, we're going to be working with implicit equations where the relationship is implied. Here's an example. Looks pretty crazy, right? X squared plus y squared equals 1. So what's the problem with that? I can't really solve for y. I mean, you could, but you'd have a plus minus, and we don't want to take derivatives of that, right? Here's another one. Xy plus y squared equals 3. You can't solve that for y. That's impossible. Okay. Here's one more. X times y equals 1. Those are implicit. And what we're going to do is we're going to use something called implicit differentiation. Okay? And here's how it works. Step 1. Differentiate both sides with respect to x. This is important. With respect to x. All right? Remember the y prime for any term involving y. Now, you guys, I'm actually not going to use y prime for most of these. I'm going to use dy dx, and I will tell you why in a minute. You're probably going to be like, that's annoying. Y prime is so much less to write, and I agree it is, but it's harder to see what's happening. Okay? So I'm going to probably use dy dx. And then it says, all right, collect all the dy dx on one side of the equation, factor out a y prime or a dy dx, and divide to solve. Seems like a lot. Okay, let's just start off. If you guys want to take a quick second, at least look at like 1 through 4. If you want to pause this and do those yourself, go right ahead. Otherwise, let's just go through these. Okay, let's use some very good notation. Dy dx equals 1. So what that says is the derivative of y with respect to x, okay? Dy dx equals 2x, right? Okay, this is a chain rule, all right? Okay, so let's get our brains warmed back up again. Dy dx equals, so the outside goes 2 to the first times the derivative of the inside. Derivative of the inside is 2. So that's my chain rule right there. Okay, here's another chain rule. Dy dx is 2, that stays the same, to the first, and then derivative of the inside, which I don't know what that is. I'm going to take away that to the first because, I mean, it kind of looks like a prime, and that's not that. So, okay, another chain rule. Now, dun dun dun, what on earth, how do we do this? Well, if we kind of follow the patterns and we know that these are essentially like dummy variables, meaning I can use whatever variable I want. And if it was like y equals x squared, it's dy dx. So if it's x equals y squared, would it be like dx dy? Because that's the derivative of x with respect to y. Okay. Okay, but we're usually looking for dy dx, right? So, wow. Oh, we're going to leave it like that for a minute. I'm going to talk about this one. Okay. Yeah, you guys, what if I just did the reciprocal over here? Right? I could basically turn this into 1 is 2y dy dx. Now let's take a look at this for a second, all right? Let's just take a quick look. Okay, look. The derivative of x is 1. The derivative of y squared is 2y. So why does it have a dy dx there? Well, because I'm taking the derivative with respect to x. With respect to x, okay? So let's try this again. This is actually what we're going to be learning today. Now, if I am taking the derivative with respect to x, I go like this, okay? The derivative of x is 1, and I took the derivative of x with respect to x. The derivative of y squared is 2y, and I took the derivative of y with respect to x. Why am I not writing this one? Because it literally just says dx dx, and that doesn't, mean anything, so we just don't need that to be there, okay? Now, we're going to get to the point where you're going to use lots of different letters, not just x and y. So, for example, if I'm taking the derivative of, you guys don't have to write this down, we'll get to this later, but like a squared plus b squared plus c squared, or equals c squared, with respect to x, the variables that I'm going to use in my answer are going to be like dA dx, dB dx, dC dx, because it's with respect to x. Okay, if we were taking it with respect to z, it would be different. All right? I know this is a kind of a new concept, but I think you guys will get this. Okay, now we just jump right in. All right, you guys, luckily this is just adding some different parts, so I go like this, okay? I can do each term separately. 2x dx dx. Do I need to write dx dx? No, because that's just 1. Okay, bring that down. 6y squared dy dx. Do I need that there? Yes, I do, because I'm differentiating to a letter other than the letter that had the derivative, right? Okay, this next one, the derivative of 3x is 3. I don't need the dx dx. And be careful, you guys. Everybody always messes this up. That is a constant, right? What's the derivative of a constant? 0. Okay? Now, we got to solve for dy dx. This one doesn't look too bad. There's some that are like a little bit more difficult than that. But basically, here's what happens. Anything with a dy dx, we keep on the same side. Anything without a dy dx, we move to the other side. So minus 2x minus 3. Okay, so I have negative 6y squared dy dx equals negative 2x minus 3. And then I need to solve for dy dx. So how do I get dy dx by itself? Okay, I divide both sides by negative 6y squared to cancel that out. And this is my derivative, which I found implicitly, okay? Because I couldn't exactly solve for y on this. I mean, I kind of could. I could bring all the x's to one side and divide by 2 and, cube root it, but that would be really awful. That is a really nice way to do that. All right? Great. Let's look at another one. Find the slope of the line tangent to the graph of blah, blah, blah. Slope of the tangent line means derivative. And this one's telling me at a certain point. Okay, that's cool. Let's go ahead and do the derivative first with respect to x, okay? X squared is 2x dx dx. 4y squared is 8y dy dx. And the derivative of 25 is 0. Now, you can do this one of two ways, okay? You can plug in x and y first, okay? So here's x, here's y. I could plug those in. So I can go 2 times 3 plus 4 times 2 squared equals 25. So, oh, I'm sorry. I was like looking at both different equations at once. Let's try this again. Okay, I'm plugging it into the derivative. Let me keep my eye on that. Okay, 2 times 3 plus 8 times 2 dy dx equals 0. So that means 6 plus 16 dy dx equals 0. Subtract the 6 over and divide by 16. So I get negative 6 over 16, or negative 3 over 8 if you want to reduce. Okay? So that's one way you can do it. Another way, I'm still using this crappy software, guys. Hold tight. All right, so here we go. So here's another way to do it. Okay? Instead of little bit bigger. Plugging in x and y first. The other way that we can do this is solve for dy dx first and then plug them in, okay? Well, if I was going to solve this top equation for dy dx, first thing I would do is I'd subtract the 2x to the other side. So I would get 8y dy dx equals negative 2x. Okay, to get dy dx by itself, I would divide both sides by 8y. And I get dy dx is negative 2x over 8y, which I could reduce to negative x over 4y if I wanted to. And then at the very end, you guys, I would plug in x is 3, y is 2. Okay, and so I get negative 3 over 4 times 2, so I get negative 3/8. All right, so those are two different, if you have numbers that you're evaluating at, those are the two different things that you can do, okay? Let me kind of show you something real quick. Okay, so I just want you to know what we're doing. All right, so what we have is we have this graph, x squared plus 4y squared equals 25. If anybody knows what that is right off the bat, but without graphing it, you're amazing, great job, okay? It's close to a circle because that's x squared plus y squared, but because I put a 4 on one side, it's actually an ellipse, okay? So I've got this ellipse. There's a point on this ellipse. It's the point 3, 2. Go ahead and label that point right there. All right, and I want to find the equation of the tangent line that goes through that point. So I went ahead and just set up the equation of a tangent line here. I don't know what m is though. Okay, so as I kind of go around with m, you can kind of see, okay, how am I going to make this tangent line? Let's see, I think we need negative. It's like right about there, I would say. Okay, what did we get? Negative 3 over 8. I feel like I was pretty dang close. Negative 3 over 8. Look at that beautiful equation. The tangent line coming right through at the point 3, 2. Okay, so we just wanted to find the slope of that line. All right, nice. Now we get to the tricky stuff. Okay, are you guys ready? This is, let me show a couple. Okay, a very, very tricky problem. But this is the majority of what we're going to look at. All right. The part that's really tricky, you guys, is this part right here. Everything else is really not bad. Like the derivative of x third is 3x squared. Derivative of y to the third is 3y squared, and the derivative of 5x is 5. Nothing too tricky there. But the question is, what do I do with that? Okay? And I will tell you what you have to do with that. It's kind of a big bummer, you guys. You have to do a product rule with just this part right here. All right. Now here's what I use for my two products. When I'm doing a product rule here, I'll use negative 2x as one, y as one. Because we got like two different variables that we're using. All right. So here's how it goes. 3x squared, that was that one. And then I have to do a product rule. So derivative of the first times the second, first derivative of the second. Okay. This product rule, this whole thing, is going to come from the part that I highlighted there. Let's like finish this out just so that we can kind of go back and just focus on that. Derivative of y to the third is 3y squared dy dx. And the derivative of 5x is 5 dx dx. But we don't put dx dx, okay? So I just need to get this product rule here. All right, guys, remember, product rule goes derivative of the first. What's the derivative of negative 2x squared? Negative 2. Times the second. And the second is just y. Now, do I have to put anything on this? No, because the derivative of negative 2x, it's negative 2 dx dx. So I'm differentiating with respect to x, so that's fine. Okay, then the next one, I put the first as it is, 2x, and then I have to do the derivative of y. Okay, the derivative of y is 1 dy dx, because I had to take the derivative of y. Okay, so let me kind of put this all together. 3x squared minus 2y minus 2x, and then this is dy dx, plus 3y squared dy dx equals 0. Okay, now let's kind of go back to these steps. And that's right. And you're going to look at this and you can see like a bunch of terms. It's exactly what we want. Differentiate both sides with respect to x. Remember the chain rule, so that means the dy dx, okay? Collect all the dy dx on one side, and that means put everything else on the other side, okay? Doesn't matter which side you go to, it really doesn't. I'm going to go ahead and leave these here, just because they're already there, and I'm going to move these to the other side, okay? So I'm going to just rewrite this exactly. When I subtract that over, I get negative 3x squared. And then when I subtract this one over, I get minus plus 2y. Okay? The next part said to factor out a dy dx. Because if you guys look right here, all right, that has a dy dx and that has a dy dx. And how am I supposed to solve for both at the same time? So what I'm going to do is factor out a dy dx. And then my last step is, because I'm trying to solve for dy dx, I divide by negative 2x plus 3y squared on both sides. And that's my final answer for dy dx. Okay? Oh, now this says, let's go ahead and evaluate that at the point 1, 2. Okay, well, that's fine. X is 1, y is 2. So if I'm evaluating this at the point 1, 2, it would be negative 3 times 1 squared plus 2 times 2. Negative 2 times 1, and then 3 times 2 squared. Okay, so I'm going to get negative 3 plus 4, negative 2 plus 12, 1 over 10. All right, and that's the slope of the line right there. Okay, that is the hardest type of implicit differentiation that we're going to do. That right there is the hardest type. Okay. Okay. Let me scooch this over a little bit. All right. Next, let's go ahead and look at this equation right here. Now, this asks me to do something a little bit different. Find y double prime. Oof, that's going to be rough. Okay, here we go. First shot. The derivative of x squared is 2x dx dx. We don't need that. Derivative of y squared is 2y dy dx. We do need that. Equals 0. Okay? Derivative of a constant is 0. This one's being real nice to me. They could be a lot meaner than this. This is being real nice to me. Okay? Because when I try to get the dy dx by itself, I get that 2y dy dx equals negative 2x. And when I go ahead and divide over the 2y, here's what I get. You can cancel out the 2's if you want. Again, we don't really simplify it unless it's going to make the rest of the problem easier, which this is. So, okay, I get negative x over y. Now, you guys, that is the first derivative. Now, I need to go again. Round 2, baby. And the way that we write second derivative in this step, hold please, okay, is we write d2y dx2. That's just a notation. It means second derivative. Same thing as writing y double prime. Okay, second derivative. Now, you guys, whew, what rule do I have to use on this? Some of you will know. Are you yelling it at your screens right now? We are going to use quotient rule. We have to use quotient rule. Rough. Okay, here we go. This is going to be tough. Here we are. The derivative of the top, that's just negative 1 times the bottom, minus the top times derivative of the bottom. Now, the derivative of y is 1 dy dx. Okay, I need to be able to see that a little bit better. So 1 dy dx all over the bottom squared. Okay, so here's what I have. Negative y minus a negative. I think I'm cool to just say plus right there, yeah. Plus x dy dx over y squared. Now that answer is correct. But typically, what it'll tell you, and it does right here, in terms of y. All right, cool. Is this, I should have written this down, d2y dx2, second derivative in terms of y. No, it's in terms of dy dx, okay? It actually should have said in terms of x and y, okay? In terms of my variables x and y, all right? So check it out, you guys. Instead of writing dy dx right here, do you know what I can write instead? Well, let's go back and look. What is dy dx? Oh, that's dy dx right there. Okay, so I have negative y plus x, negative x over y squared. Are we trying to simplify this? I don't think so. I think I'm fine. Okay? So when you do the second derivative, you got to use part of your first derivative in there. All right, last question real quick, just a little bit more of a interesting implicit question, okay? All right. My friends, whew, this is rough. What's the derivative of cotangent? So derivative of cotangent is negative cosecant squared of y. But then this has a derivative too, right? dy dx. So it's still like chain rule. Any y is going to have a dy dx. Okay? Okay. That's a times. All right, the derivative of x is 1 dx dx, and then the derivative of y is 1 dy dx. All right, now here's the thing, right? We want to get our dy dx's on the same side. That's that term, and that's that term. So I'm thinking I might as well bring this over, since my number itself was already on that side. So positive, when I add this over, it's going to become positive 1 dy dx minus cosecant squared y dy dx equals 1. Okay, check it out. I have a dy dx here and here. So what do I do with that? I factor it out. And then last but not least, I divide for dy dx, or I solve for dy dx, sorry, by dividing that over. Okay, so here's my final answer. Dy dx is 1 over 1 minus cosecant squared y. Okay? Little tricky, but hopefully you guys understood that, and we're going to be doing a lot of these types of problems in class, these implicit differentiations, all right? Cool.